So we'll get started. There's another presentation immediately after this, a short little blast from the O player. So try to get through some of this a little bit quickly so we have time for some Q&A if you guys want, and make sure that they have time to give their spiel. So a little bit about myself. I'm Andrew Crowe, lead engineer in video development at Limelight Networks. I figured I'd start off. A lot of people are giving some about me stuff. I don't have a slide for it, but just to give some history of where I come from. I got my start in development in defense contracting, doing flight simulation stuff, and transitioned from that into video with UAVs, unmanned aerial vehicles, so things like Predator, Reaper drones, that kind of stuff. And I bring that up specifically because what we were doing with the UA video at the time was standardizing it. So the Department of Defense said, hey guys, here's the standard that you need to adhere to. Basically, MPEG-2 transport stream. The old standard for metadata being this thing called EG 104, Engineering Guideline 104. It wasn't really a standard. It was just kind of a rough guideline. They improved on that, made KLV 601, so it's a bit better of an actual standard that you can adhere to. There's real documentation, real test frameworks and things like that. And the whole world was happy and everybody adhered to the standard, right? That's the normal thing, except that Lockheed Martin, Northrop Grumman, Raytheon, and all those said, well, that's great. We appreciate that you have a standard that you've designed, but we're going to do our own thing, and you're just going to deal with it because we've already built this multi-billion-dollar product, this drone. What are you going to do, not buy it? What are you going to take the money back? So the government had this product to essentially take in all those different UAV streams and normalize both the video and the metadata. No audio, because the audio from a UAV is just going to be so it's just video and metadata. And we would take that, fix it up because it would always be slightly wrong. They would be using the wrong math. We could detect the location that you're saying the top right corner is impossible based on the location of your craft and the direction of your camera. So we'll calculate that ourselves and put it back in the correct format, send it on out. And this is all done in MPEG-2 transport stream. And the software that was doing this normalization was hard-coded from its inception to do 1-minute segment sizes. So you had a 1-minute delay before you could do anything with that. And so this is running on old Windows machines that aren't really powerful anyway. So once you're done writing the segment to disk, then you have to have something take that from the disk and ingest it into some analysis tool. And shortly after I started, as I learned the transport stream specification, as I learned about GOP sizes and things like that, I was like, why are we statically doing this at 1 minute? That doesn't really make sense. Shouldn't we make this configurable? So we did a release with an unplanned feature of adding a little slider to change your segment size that this normalization tool was outputting. And freaking generals were freaking out. They were like, oh my God, we can go less than 1 minute. We can go down to 10 seconds. And like, yeah, you can actually just nudge it a little further. You can go down to 2 seconds. They lost their damn minds that they could get 2 seconds of video at a time. They didn't understand that it was feasible. And this was 2011, 2012, so not that long ago. And this is the military. This is analysis of actual combat footage, things like that, where it's really important that your analysts get that data quickly. And so I just wanted to relay that anecdote of this has been a problem tackling latency. The presentation's titled here, WebRTC Overview. In the booklet, it's called Tackling the Low Latency Problem or something like that. And the presentation before me in this room, I don't know if anybody was here for this, Dom was talking about multicast and how we had actually solved the latency problem in the 90s, and then everybody got real hot onto HTTP and CDNs, and he had a lot of choice words to say about telecoms and CDNs. But we had kind of solved it, but then there was a lack of trust, and so we built up this trust in HTTP, and now we're trying to resolve the latency problem, again and again. It's always trying to chase latency and rectify it against quality and stability. and trying to determine from the user perspective when you want latency, ultra low latency versus when you want quality. So, kind of an unplanned anecdote there. Overall agenda, I'll tell you about WebRTC. Is anybody here familiar with WebRTC? Have you heard of it? Anybody actually used it? So I would venture a guess that everybody in this room has used WebRTC, not maybe from a programmatic standpoint, but you've interfaced with it 100%. So we'll talk about that, some of the history of it, a little bit about the APIs, why it's real time, and then we'll talk about Limelight and what we're doing that's different. Not trying to do a sales pitch. We've got a booth over there. If you want the sales pitch, you'll find me over there after this, and I'll give you that whole spiel. So I'm actually going to tell you about which of the protocols that we're implementing and why, and what we're doing to do this WebRTC thing on a global scale, and how that's different from anybody else. And hopefully we can get some cooperative discussion going on, and figure out some of the solutions to the problems that we're hitting on as we continue to tackle the latency problem. We'll wrap it up depending on the time left at the end, with some avenues that we're looking for further research and discussion. So we'll hop in. So history of WebRTC, the first implementation was in 2011. So about the same time that we were freaking out generals with low latency transport streams, Ericsson and Google and a couple other people were working on this thing called WebRTC. The first actual implementation, I believe it was Ericsson in 2011, and then Google shortly after that open sourced their implementation of it. And then a couple years later, as people kept working on it and improving it, as the standard got more well-defined, they integrated it into their own product. So Hangouts, the chat that's right there in your Gmail window. When you do a video call or an audio call with somebody on Hangouts, in 2014, that started using WebRTC to do that peer-to-peer communication. The other key thing that shows how large this is Microsoft actually said, hey, we want to be involved in this too, and they figured out some improvements to the object APIs so that you can do arbitrary object data sharing, whether that's command and control things, so you can move a camera around, or it's just chat data, so that you're communicating with somebody, so that maybe you don't have to have an XMPP chat channel and a WebRTC direct peering video conferencing. You can kind of use the same protocol here for all of that. So really, WebRTC was designed and initially implemented to be a peer-to-peer implementation. So person-to-person, web conferencing, Hangouts, Skype, that kind of thing. So it deals with things like NAT traversals. So when you're in a hotel and you need to have a conference, the hotel's not going to have an IP address for every room. You're going to have to go through a NAT. That gets really complex. So WebRTC, that was one of the first things that they decided they needed to cover. There's some stuff with connectivity, making sure that the person that you're sending things to is actually there, because it is on UDP. So you are typically just doing a fire and forget, but periodically you need to check in, make sure they're still there, so you're not just sending data to nothing. Yeah, so we'll just keep on going. Yeah, maybe. Maybe I broke something. Hello? All right. Let me exit out of slideshow and restart. Is anybody a PowerPoint expert? Hello? There we go. I tabbed out somehow. Okay, so why WebRTC? Kind of touched on a little bit. It's real-time data transfer. So the data that we're interested in this case is audio and video data. it's in active development as a standard, which is always nice. You have a 1.0 version now, but it's going to be continually improved upon. So you can give feedback to the working group and say, hey, I've seen this detriment or this gap, and I think this is what we should do about it. You can talk to IETF. You can put submissions in as it's in active development. There's a standard API. It's baked into most browsers right now. So when you want to do a Hangout session, you can trust that Chrome can do it, Firefox can do it, Safari can do it. They can all do that kind of things. So you're using these APIs like RTC peer connection and RTC data channel to get through that NAT traversal, to get directly connected to a person, to send them data. And then, of course, it's open source. Google started that trend with this product back in 2011. And so there's all kinds of examples out there. There's around 1,400 or so active development projects using WebRTC right now across the world. So taking a further look at the ubiquity of this technology, at a conference in 2018, some of the engineers at Google were reporting on the usage rates, specifically in Chrome. So 1.8 billion minutes of audio-video transmission over WebRTC in Chrome alone in 2018. So I like to say it's 180,000 minutes per minute, which is pretty impressive. That's everywhere. So that's not even talking about Firefox or Safari or whatever Microsoft browser they have now. Facebook, integrated it into Facebook Messenger, Facebook Live. It's kind of in WhatsApp. It's a little bit of a hodgepodge solution, a little Frankenstein, and Facebook doesn't have isn't giving numbers on minutes or hours used, but they're saying we're looking at 400 million users per month on WebRTC. So you've got other companies like Discord and Slack for their quick web conferencing things as they're trying to take over the world. Everybody's on Slack. Slack calls are great, right? They're always super reliable. And some of the success is because of WebRTC. Some of the struggles of that is because they are learning WebRTC as they go and encountering some of the things that we've also encountered. So kind of a nice graphic chart of the support in browsers for WebRTC. And you can see all the Google and the open source stuff down at the left side, the most well-supported, most comprehensive support. You're looking at your two primary codecs for this that are mandatory, that are defined in the specification that the browser must support, that WebRTC data flow must support is VP8 and H.264. Google, of course, loves VP9. They're a big sponsor of it. It's in YouTube now, so you've got that support in Chrome by default. Firefox followed quickly behind with that. On the right side, you've got Safari, because Apple was kind of not that interested initially. They were thinking, well, we're just going to solve this problem with HLS, and we'll start looking at low latency HLS. So they also have their own preferences for video codecs. So there's no VP8 support in Safari, so that's why it's got the yellow and the red. Is they don't have the mandatory support for VP8. They do have H.264, which is more common, so you can still use it. Hangouts does use H.264 by default, I believe, or at least it's when you're connecting to somebody from Safari, it might do some logic there. And there's been a fair amount of bugs reported against Safari on their WebRTC implementation. So they are working on it just slowly because they're much more concentrated on HLS and especially low latency HLS. So the APIs that you're going to use to make this thing work is you're going to look at your media stream. That's going to be your primary source. Your audio video is going to go over your media stream. There's APIs to create that stream on the creator end, and then on the receiver end, you're doing APIs to get that. Physical would be your microphone and camera on your phone or your computer. You can access local files for sending just a raw file, or potentially in the future doing some kind of VOD to live type solution with WebRTC with that file access. One thing to note here with the network source and some of the APIs is you're going to be connecting direct to an IP. So even if you're on a VPN, if you're trying to protect your privacy, because the UDP backbone of this, because the backbone of this is all on UDP, you have to have that IP address in the clear, and it's going to resolve to your actual IP address, not the VPN IP. That's going to be kind of the proxy. So if you're doing something nefarious, don't use WebRTC because you can be spotted out. On the peer connection, we don't need to get too far into the details. I think everybody's had enough time to take a snapshot of this slide if they want to. The data channel is really interesting. The keyword here is arbitrary. There is no real definition of what data means here. It's a data. Do whatever you want with it. Do chat. I don't care. Do command and control of your camera. Do sports betting. Make a game if you want. Do Twitch plays kind of thing with this. It is an arbitrary data channel. You can do whatever you want. So it is very similar to a WebSocket, which we'll touch back on when we get around to Limelight's implementation. And we'll just keep going. So what makes this WebRTC stuff real time, and I mentioned it last slide, is UDP. So TCP is the most ubiquitous out there. It's got the handshaking. It's going to make sure you got that when you're doing VOD content, when you're watching Netflix. If you drop a packet in the middle of your 12,000 packets that you're getting for video and audio data, if you miss one of those, it's going to affect your playback quality. And you're watching VOD, so you would prefer that your player just go and get that request or get that chunk back again. If you're doing live, you may not care as much. You may want to just say, screw it, it's gone. We're going to keep going this way, guys. And things are falling out of your car. It's fine. You're going forwards. But in this, with UDP, you end up with the flow control, congestion control, things like that, of knowing what your user is experiencing. How do you get that data? There's a portion of WebRTC that's built for that. Parts of it like the REMB, which is the receiver estimated maximum bit rate, so that you can determine what you need to send to that player, which is important for doing ABR ladders. If you want to do multiple bit rates of WebRTC, it's not defined in the spec, but the spec shows you how you can do it using things that it provides to you, and you just have to do a little bit of customization on your end. So WebRTC is using, it allows for you to use DTLS over UDP, so you can encrypt your UDP content. So if you're doing something nefarious, you want to use DTLS, but your IP will be exposed, so you're kind of half and half. Not that I'm advocating for nefarious things, just I like that word. So we have SRTP, SRTCP, and then SCPT for that arbitrary data channel. Just a note there that it is often neglected. We are one of those people that do neglect it as well, but we have seen some really interesting customer use cases popping up as we've deployed our product and gotten people on board. They're finding ways to use it. So DTLS, datagram transport layer security. It kind of sits on top of UDP. There's a key exchange here, so you can do a secure key exchange. Then that allows you to do encryption of UDP packets as they're going out, so that whoever is, nobody can do a man-in-the-middle attack there. As part of that key exchange, we're doing self-signed certs, so you don't have to deal with some certificate chain. You don't have to go to VeriSign for your Hangout session. You don't need the absolute authentication to say, I am who I am. We just need to know that this connection is secure because nobody else has your cert. We're good to go. And then the other important note here is that we're using block ciphers and not stream ciphers. So block cipher, you can do individual kind of fragment chunks, whereas the stream ciphers require that in-order delivery, or else nothing can be decoded. SRTP as the secure real-time transport protocol, and then SRTCP is the secure RTP control protocol. So secure real-time transport protocol control protocol. So SRTP is kind of, again, sits on top of UDP. It's got the encrypted payloads. Your headers, your metadata for that stuff is not encrypted. So this is where your IP is going to be exposed. This is where some of your other things might be exposed. So you want to be aware of that. You're only ever encrypting your packet data. So there's an area for improvement if somebody can figure out how to do UDP full packet encryption. You've got a moneymaker. The SRTP is where you're sending your audio video data. And SRTCP is kind of a flow control to make sure that you are sending your packets in an efficient manner over UDP. And it's kind of on the outside. It sits still kind of in UDP, but right next to SRTP. So this is where we get the statistics of our SRTP packets, like the REMB. We get things like jitter, so we can know what's our, how's the timing looking? Are we getting a bunch of, frames that are timed really close together, and then one that's timed really far, and it's going to look weird? How's that looking with our PTS number? Well, we don't really have PTS numbers here because it's not transport streams. Sequence numbers and that kind of thing, so you can track from the player side, are you dropping any packets? We can track that, and the player can then report back to us via the SDK that there's some problem, and we can get a notification, go in and look and see, is it on our end, or is it last mile ISP? Is it the mobile device just not being able to cope with something? They're also playing Hearthstone while trying to stream, and they're on an 8-year-old Android phone, and why are they trying to do that? We shouldn't care. The other that often neglected data channel, SCTP, is the stream control transmission protocol. And so this is peer-to-peer data exchange. So when you're conferencing with somebody on Hangouts and you want to send them a file, you're talking about a file, you're doing a screen share, and they say, hey, actually, can you send that to me? It's hard to see it. I'd like to pull it up on my screen. You can send it over that. This is, again, tunneled over DTLS, just like the media packets are. But it's kind of a weird thing. It's not quite TCP. It's not quite UDP. It's somewhat configurable resiliency of UDP. You kind of take UDP, add an extra layer on top of it. That's a little bit more configurable than TCP, which says every packet must come. If I don't get a packet, I'm not going to proceed until I get that packet. That's not exactly how TCP works. But SCTP, you can configure, like, if you don't get it, try again. Well, we still haven't gotten it. Let's move on. You can do some of that configuration there. So I'll take a note here and say this is a little table I got from bloggeek.me. Really, really great resource for WebRTC knowledge out there. A lot of information about implementation, about some of the protocol specifics, a lot of examples. Really comprehensive site. So just a shout out to that person or people. So what makes Limelight unique in this space? Because, as I said, there's 1,400 or so projects using WebRTC right now. So what makes us unique is that we're already a global CDN. We have servers in POPs all across the world. We have a CDN product that does all the typical HTTP caching and delivery with origin shield architecture and live streaming integration, all that fun stuff. So we're able to utilize some of our backbone to make sure that when we're transiting data, that it is unmolested and high performance and of the utmost importance to our network. So we set the quality, the QoS level at the highest, so it's going to take priority over a Microsoft update, for instance. We are also able to leverage our DNS products because they're integrated into our system. That actually becomes a key part of figuring out ingest and edge egress locations to make sure that we're getting our ingest and our egress as close as possible to the creator and the consumer. Because we have this scale, we're able to do redundancy as we do for all of our live streaming products. We have redundancy at all stages. And of course, we have this existing live streaming expertise. We've been in the game for a while, And as other CDNs tend to be shifting their focus more towards hardcore security, we are realizing actually we're pretty dang good at this video stuff. We are pretty much the premier CDN for delivering video bytes. We've got customers like Amazon and HBO and Disney that trust us to be high performance for their premium clients. And that kind of leads into the dedication. So we've got that dedicated hardware and network backbone. We've got a dedicated development operations and support staff for this product. And then we have our customer integration teams with SDKs and stuff like that. The traditional WebRTC workflow is kind of over there on the left. Peer-to-peer, you can have multiple people in your Hangout session. You can have, I'm trying to remember the name. It's one of the new kids apps that's all the rage, like House Party, I think. I feel old. But that's the type of thing that WebRTC was initially designed for. And we're looking at that and saying, yeah, that doesn't work for a CDN. So what we are doing is essentially leveraging our CDN to broadcast out. Not quite multicast like Dom was talking about last presentation, but we're using a system of ingests and relays to kind of replicate that environment. We have some fallback mechanisms to go to HLS or Dash if you can't do WebRTC. So we still have low latency, not ultra low latency streaming. And then we have some fallback patterns as well because we have RTMP expertise. If you end up with a customer on Safari or the latest version of Edge that can't connect because they haven't implemented the WebRTC just exactly right, or there's some problem with NAT traversal, you can fall back to RTMP from our Edge. So a little bit more graphic about that. You've got your video source coming in. We have, again, with this redundancy, we always offer our customers the ability to do dual ingest. They're always in separate locations. So if you are in North America, if you're on the East Coast, you're wanting to do a stream, your primary ingest may be in IAD, which is going to be DC, and your backup may be in New York. All right? And so that way, if we're doing maintenance on some server, we can take down your primary ingest, and you don't even know. If your connection to one of those gets severed because some ISP, you don't even care. You'll just reconnect when you can reconnect. We can reprovision that dynamically if there's some systemic problem so that you can get your secondary stream back up quickly. But we're essentially taking that RTMP ingest and proxying it over to the edges. And so what's not shown here is a series of microservices that are managing these streams so that we know which ingest has which data coming in, which edge needs that data, and which relays are in the middle and have capacity to kick that over. So each relay does add a little bit of latency as you're receiving that in and proxying it over, but it adds a huge amount of resiliency and stability. So that 1 to 4 milliseconds of additional latency is a fair trade-off. And then on the edge, we have these edge nodes all across the world in our POPs that the consumers, whether they're on laptops or mobile devices or whatever, can connect into. See how I'm doing for time here. And so everybody's favorite thing in presentations is sequence diagrams. Actually, I'll take that back. Everybody's favorite thing is code snapshots. So this is second favorite. So just a quick example of the series of steps that has to happen. This is from a viewer perspective, right? So on the left, you've got your viewer. This is the person that wants to watch your broadcast. I want to tune into the NASCAR event, and I want to make a bet about the speed of the next pit stop. Or who's going to have the next wreck, or I'm watching football and I want to make a bet on the play, or I'm watching a celebrity game show and I want to interact with them. So I'm the viewer all the way on the left. So the very first thing we're going to do is connect into our DNS. So you go onto your customer site, your whoever you're going with. For the early example, NASCAR. You go to NASCAR.com. That's going to route you to this web page. The web page is going to resolve to our DNS. Our DNS is going to do a geolocation to figure out where you are and figure out which one of our edge nodes is closest to you. So we want to be as close to you as possible so we have the least amount of local ISP last mile hops, because we don't trust those, we trust us, and we want to do as much on our system as possible. So we use HTTP GET to do a subscribe call. That goes into our CDN, which gets a 302 redirect back out to the viewer, follows that redirect over to our one of our Java microservices to do the subscribe. The subscribe response gives you back a list of edge nodes that you can connect to, and a little bit of data about that channel. So some of the metadata, here's what you should expect, here's the bit rates, here's how long it's been running. When you get that list back, the first thing that we're going to do with our SDKs is actually open up a WebSocket connection to that edge. And so we do that. This is outside the spec of WebRTC, but we're doing it rather than doing it with the SRTCP. We're doing it with WebSocket connection, and it's a secure WebSocket. That's the second S. And we use that initially to start the stun request. So stun is, I'm not going to try to remember it off the top of my head. It's a NAT traversal tool, or it's an initialization to start the ICE negotiation. ICE, again, I'm not going to try to remember it because I just had lunch and my brain's starting to go to sleep. So we open that WebSocket connection to the edge so that we can do this NAT traversal negotiation. We maintain that WebSocket connection for data channel. So we, as I mentioned, that often neglected data channel, we're neglecting it too. So we're not using it for our services, but it is there for anybody that's using our product if they want to use it. It's just not something that we're using for command and control and monitoring of the system. So once we get that ICE negotiation completed and we get connected to the edge is going to say, well, I don't have this stream yet. I can't give it to you. So the edge may talk back to the Java microservice that's going to tell us which relay is likely to have this stream go into it. So we'll connect to a relay. Maybe the relay does have the stream. Maybe it doesn't. If it doesn't, it's going to connect back to that Java microservice to figure out where it should go, whether that's a relay or the actual ingest. And so you'll do that a couple times. These take a few milliseconds because it's all internal to our network. You're going to have your edge subscribe to the relay. That's going to be an RTMP stream. Your relay is going to subscribe to the ingest, and it's going to just bounce back along the way over RTMP. When it gets to the edge, we're going to take that RTMP stream, convert it to the WebRTC using DTLS UDP, and we send that out, and that's the magic there. And then we keep that that control channel open on WebSockets, and we use some of that for the player, the SDK, to report back. What's our current REMB, what's our jitter looking like, how many frames are we dropping, and we can log some of that internally and monitor that so that we can know when we need to react to poor quality, if at all. So we've had some success with customers. I mentioned some example use cases. Really, when we started this project up, we were looking at the initial very obvious use case is sports betting. If you're going to do play-by-play betting on an NFL game, you need to make sure that the person making the bet has all the information they need and that they're not betting after the thing has already happened. As you can see this at large-scale events, radio is the lowest latency. It's you just stream it out into the atmosphere, it gets there. So if you're doing betting based on traditional HLS, and you're trusting that the person's getting that, really quickly, that's still going to be 10 to 20 to 30 seconds behind a radio broadcast. So somebody listening to the radio could get the information, make the bet, and kind of game the system. So you need them to have as low latency as possible. So that's our base use case, is kind of sports betting. Not the most glamorous thing. I'm not a big fan of the gambling aspect of things. So it's been really exciting to see what our customers have come up with. We've seen some interest in offshore oil rig inspections. You used to have an inspector go out and climb down the scaffolding, rappel down, looking for rust or bolts missing and that kind of thing. Several years ago, they switched that up to have a drone, a quadcopter with an HD camera. So you have a drone pilot out there, and then the inspectors standing next to them watching the feed, and they're looking that way. So it's actually substantially safer, but you're still sending multiple people out to the site to do the investigation, the inspection. So what if you could just have those people in an office park in Houston? Well, you're going to cut down on your costs, so you're not going to have them travel out. You can have more inspectors looking at the video feed. You can train inspectors on these video feeds in real time. And you're also going to cut down on your liability insurance because you don't have these untrained people coming out messing around with drones while you're trying to do work on your rig. And you need that to be ultra low latency so that you don't crash the drone into the rig and cause a big fire and an environmental hazard. We have one customer in Asia, I think Japan, maybe Korea, called Live Park that's doing a celebrity game show. So something, as it was described to me, something kind of similar to like Big Fat Quiz of the Year, if there's any folks from across the pond or that are fans of that, where you have kind of celebrities on a panel with a host, and it's more of a comedic thing than really a game show for prizes or anything like that. We don't really have anything like that in the States because we're so big. You can't really get the best celebrities to all come to one spot on a whim for this 1 hour event that they're not going to be able to promote their own thing for. So they were seeing a similar problem in Asia with not being able to corral these people in. So let's use real-time streaming to give each of these celebrities a camera or just their phone. They'll stream in, so they establish multiple connections. They'll have a broadcast feed that kind of muxes those together and makes an end product really quickly, and then the viewers can decide which celebrity they want. Do they want to watch the mainstream? Do they want to switch to celebrity A, B, or C? They can give feedback. They can applaud in real time. They can give clues if the celebrities are doing some sort of like scavenger hunt challenge. Their fans can give them clues via the shared data channel. So there's a lot of interesting areas for this larger scale, ultra low latency WebRTC implementation to be used in, and we're seeing some good stuff. We've had some successes. We have some misses that we've learned from, and we're working to improve that, like regionalizing these things rather than having one global thing. We can kind of tighten up the regions and then have individual specialized proxies to go. If you have your event primarily in North America, you want that to be isolated to North America so that a large event in Asia doesn't impact you. But you wouldn't want to isolate that completely out and say only North American viewers can see this stream because it's originating. So we have some regionalized with some proxies through that we're working on right now. And areas of interest just in general, that shared data channel kind of presents a challenge at scale. One of the reasons that we don't use it as part of a core is it's really a memory leak waiting to happen. It is a memory leak. It's just whether or not you use it. If you have 5,000 people viewing an event on WebRTC and you allow them to do peer-to-peer as is designed and do shared objects and data exposure there, one person can take everybody down. And we don't want that, so we have some limitations there to make it more of a broadcast thing and a little bit safer for people to be able to share things back in a little bit more controlled. So a note on content security. We haven't really found a use case for DRM in ultra low latency. Typically the things that you want to DRM are your VOD content. If you're doing something ultra low latency, you tend to care mostly that it's happening now and you see it now. And so if somebody records that and then uploads it to a file sharing or a torrent site later that day, well, the event's gone. It happened 6 hours ago. You can't do anything with it. You can't interact, and the value is gone. So is there really a use case for that? And beyond there maybe not being a strong use case for it, just like your IP address that gets sent in the clear over that non-DTLS encrypted headers of the UDP packets, your DRM keys would have to be sent in the headers so that the receiver could know what the heck it's receiving and use those keys to decrypt it. So, it's not, in addition to it not maybe being viable, there's still a very clear gap in the ability to do that. We've had a lot of trouble with cores. Core support is kind of been the bane of our real-time streaming, and so we tend to just allow all. So it's not really feasible right now for us to set up core support on a site-specific thing so that you can only access this stream from this particular domain. So there's also things that we are looking at. How do we do advertising on this? Almost every presentation at Streaming Media this year has mentioned advertising. If they're not talking about WebRTC, they're talking about advertising. So because we own this whole backbone and we are ingest to edge, should we be doing server side, the edge area ad insertion, or is that just going to cause latency? So we're looking at that kind of stuff. A note on the multi-bit rate, which I didn't mention in the previous slide. WebRTC doesn't have really a standard specification for multi-bit rate, so doing 1080p, 720p, 480, et cetera. So if you want to do that, if you want to try to support a variety of qualities so that you can get the widest audience possible, you have to encode it yourself in multi-bit rates, send them all in as disparate streams, and then our microservices will create a synthetic ABR ladder, is what we call it. So we can kind of synthesize the multi-bit rate style of traditional HTTP streaming. The other thing is, those client measurements, right now it's fairly limited to just some basic statistics, the receiver estimated maximum bit rate, some things about jitter, which aren't always 100% accurate, packet drops, which are after the fact, about them. So we're looking at ways to be more proactive about knowing what's happening with these streams as they're going down to the clients. And then, of course, beacons for analytics so that you can know exactly who's viewing from where. We get a little bit of that on our server side as the geo lookup with the DNS. We can kind of see and log at the DNS level that we have people requesting, but we don't know then how long that person is staying on the stream. We just know that 30 people have watched this for a total of 4 hours, all said. But we don't know individually who's who on that stream. So, getting some player beaconing in there is kind of a next step so that we can be a little bit more granular in that. And I think that's going to do it. And we have maybe a minute or two for questions before we get handed over to the O players, if there are any. Yeah. Yeah, so the question was about the ABR ladder, the multi-bit rate, and how good or how quickly it will switch from rendition to rendition. And that is actually, it's up to the server to decide it. So similar to RTMP, it's up to the server to decide it. So on the player side, as long as the encoder is doing its job correctly and having the GOP correctly aligned, we will do that switch over on a GOP boundary. And so it should be essentially transparent. You might see a little blip as the player resizes its resolution, but you're looking at essentially the same as your traditional multi-bit rate HTTP streaming. Yeah, yeah.
Any comment on the HQ trivia?
No, I put on my hipster, crotchety old man pants during that whole HQ trivia phase, and just was like, it's not gonna last. And so they are. I'm not sure exactly what they're doing. I'm pretty sure they're using WebRTC, and they're essentially doing like a series of relays. But we haven't looked at them as the exact use case that we want to support. If they want to talk to us, we'd be happy to talk and learn more about what they're doing, but they seem to have a moderately successful platform for the one extremely limited use case. And so we're trying to do something a little more generic, get our platform up and stable, and then we can start looking a little bit more at those custom things.
The question is, we talked about scalability.
So yeah, the scalability is the real problem, or the hard thing to solve here. With traditional streaming, you've got HTTP, you can cache it, do all that kind of stuff. So one of the things that we're considering with scalability is, as Dom mentioned in the previous presentation here, it was about multicast. Can we utilize multicast at the edge to maybe simplify some of this delivery of low latency streaming? That's one of the things that we're starting to look at. So yeah, we've been really focused internally of what we're doing to make sure that this solution works for our network, and we've had an eye out for that. The product people, maybe some of the folks over at the booth might know a little bit more about how we compare to that, but I've been more in the code area, so kind of just taking direction from the product folks on what we should be doing. So, all right, I think that's it. Thank you.